So we're starting to look now at what would a typical experiment for a low-pass filter, sort of low-pass filter block as we define it, which is a very simple OTA element with a capacitor in it. And so you ask the question, well, how do I start to look at this and how do I start to use it? And at one level, things can be set at can be very general. It's like we have one tool set, allows you to design, allows you to do high-level simulation, allows you to compile to hardware, and which is all very true. Now, this really now looking at this question though allows us to dig in a little bit deeper. What am I actually going to see? And the first thing is this is sort of the block diagram I would see of that circuit that would be done in an XCOS, which is of course built in the Scilab structure. Now, you'd be able to pull down something that looks like an arbitrary generator. You would say you'd have some sort of simple waveform that you would define in it, which might look like a square wave. Just define it in term, and then there's a sample that you need in the arbitrary generator. There's a low-pass filter block. You'd actually take this block, and then there's a couple different parameters if you double-click on this that you'd see. And then from this, and there's, I can maybe pull this out to an I/O pad. I could pull this to something in XCOS that allows me to measure it, and I'm actually sampling it with some clock. So XCOS is really interesting in terms of its structure because its ODE simulator allows you to deal with both continuous and discrete kind of structures very natively, which is really quite a very useful structure and was extremely useful when we put it together. So then I could take this structure and I could decide to simulate or decide to compile it to hardware. The first thing to realize is that these lines are all vectorized in the sense of they could be an input or they could be a bus. And that's really important to kind of notice in how you would approach it. And also we'll talk about, what would the simulation model? This is a level 1, so it's more of a macro model. So it means I'm not simulating every single individual transistor at a current and voltage level, but I'm actually doing a sort of model based on the device itself, looking at its properties. And so I'm abstracting those pieces together. Still, it gives you data assuming that the models are done correctly, like any other SPICE model or any other structure. Assuming that's done right, I get very, very close numbers to my experimental data, but a lot more efficient both computationally, as well as it also fits within sort of more of a data flow architecture format. Current voltage relationships are implicit differential equation solutions, and a lot harder to actually make those work, and therefore just means it takes a lot more work and I have to worry about my accuracy more. But I can imagine saying to make all these lines be 4, and therefore I have actually 4 of them. It would actually come, as a result, is instantiate 4 of these low-pass filters, and I'd have an inputs that are a bunch of different steps. I'm going to step to this one, the second one will step to this one, the second one will step to this one, step to this one, this one, this one, and this one. And as a result, I'd say, okay, what does the response look like? And I get very classical, output responses out of all of these. Nothing terribly surprising in terms of the structure that I'm looking at. Okay. I can also do this experimentally in terms of looking at this in terms of measured results. And in this case, I would also say I'm going to put in a step which is going to be 1.2 and then goes up to 1.4 volts and then goes to 1.2 based on whatever the sample is. And then these would be my experimental measured results, and you think that looks like what I would expect to see. And so, again, because I expect to see good first order behavior. Now, so this gives you an idea of what a low-pass filter is. It's a very straightforward thing. If I actually double-clicked on this variable, on this element, I can then decide how big is my buses, and I keep all that consistent. The second thing is I would say is like, oh, I need to figure out what my parameter would be, and basically what's my bias current or what sets my frequency response. This compiles to sort of a core circuit. If I actually am doing the measurements through an I/O pad, then I would measure it in one form or another. We actually have on-chip DACs and ADCs you might look at, but also just this whole conversation of an arbitrary generator. You think, oh, that's a nice, cute little block, we just drop it down. But to actually do it, it compiles through a whole bunch, through the microprocessor, through data in the SRAM, through elements in the DAC, and then it has switches to the target I'm looking for. So just kind of remember we have all these pieces there. So when we drop this very straightforward block down, there's a lot of richness to the structure.